Welcome to Spring LIB.
In this exercise, we're going to need to use the relation between the change in velocity and the acceleration. So basically, before diving into the exercise, I want to remind you how we relate these two quantities. So we have that the change in speed, or in this case, the change in velocity, which is equal to the final speed at a time t minus the speed at time t0, is equal to the integral from t0 to t of the acceleration times dt. This is all the information we need in order to solve the exercise. So basically, what we have is a motor that has a mass m and is connected to a block A that has a mass of 400 kilograms. And the motor exerts a force on the cable that is given by the graph. In the graph, we have that F of t is equal to 625 newtons per second squared times t squared. And our goal is to find what is the speed v of the block after a time t equals 2 seconds has passed. So first, what I'm going to do is to draw a free body diagram on the block A. So here we have block A, and the forces that act on block A are the gravitational force acting downwards, so that's mg. Then we have the tension, T, acting upwards, that's the tension of the cable. And we also have the normal force. Now notice that the tension that the motor exerts on the cable is different from the tension that the cable exerts on the block A, and that is because the cable is not the same. Notice that the cable upon which the motor M exerts a force is kind of folded around a pulley, this one here. Okay, and this pulley exerts a certain force over a second cable. And notice that if the motor, which is this thing here, exerts a certain force that is equal to the tension on the cable, T prime, then the tension on the cable, on all the cable, is equal to T prime. Okay, and so we have T prime and T prime. So basically, we have 2 times T prime is the force that pulls the pulley up. And T prime is equal to F of T. Okay, but we also have the force, the tension, T, that pushes, that pulls the pulley down. And since the pulley is massless, we have the 2 T prime minus T is equal to 0, meaning that the T is equal to 2T prime. So T is equal to 2 times F of T. Okay. So for block A, we have that T plus N minus mg is equal to the mass of the block times the acceleration. Now notice that when the normal force is present, the block is still at the ground. And as the force T increases, the normal force decreases while the block is still. So A is equal to 0, so A is 0. Okay. And a point, there's a point when the normal force is equal to 0. And from that point on, the block starts to move up. So we have that t is equal to mg. Now, as I said, t is equal to 2 times f of t. So at that point, 2 times f of t is equal to mg. Now f of t is 625t squared, and this is equal to m, which is 400 times 9.8. So the time when the block starts to move up is equal to 400 times 9.8 divided by 2 times 625. So this is equal to 1.77 seconds. So between t equals 0 and t equals 1.77 seconds, the block is still. Okay. So after that, the only forces that act on the block are the tension, which is 2 f of t minus mg, and this is equal to ma. So the acceleration is 2f of t divided by m minus g. Now explicitly, this is 2 times 625, so it's 1250 divided by 400 t squared minus 9.8. This is all in the metric system, so I'm not gonna bother about units. So I have 25 divided by 8 t squared minus 9.8. And the change in speed, so the speed at t equals 2 seconds, and the speed v0 at t0 equals 1.77 seconds, is equal to the integral of a, which is 25 divided by 8 t squared minus 9.8 dt from t0 to t. So I have that v0 is 0, that's the initial speed. So I have that v is equal to 25 divided by 8 times 3, which is 24, times t cubed minus t0 cubed, minus 9.8 t minus t0. So v is equal to 25 divided by 24 times t cubed. So that's 2 cubed minus t0 cubed minus 9.8 t0 minus, I'm sorry, t minus t0. So v is equal to 0.303 meters per second, which is the answer to our exercise.